This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to today's discussion. We're diving into a fascinating interactive physics simulation, Falling Rods Left Anchored / Right Free to Slide. It's a JavaScript applet designed to teach about the turning effects of forces.
Indeed, it's a great example of how interactive simulations can enhance physics education, moving beyond static textbook diagrams.
Exactly. The simulation uses a simple setup yet manages to illustrate complex concepts. What makes this particular simulation so effective?
The simplicity is key. By focusing on a single constrained system, a rod fixed at one end and free to slide at the other, it isolates the concept of torque and its impact on rotational motion.
And the interactive elements, how do they contribute to the learning experience? Let's talk about the interactive aspects. The briefing document mentions combo boxes, sliders, and field boxes allowing users to adjust parameters. How does this enhance understanding?
The ability to manipulate variables like height, angular velocity, and time step allows students to experiment and observe the direct consequences of their actions. This hands-on approach fosters a deeper understanding than passive observation. They can see, for instance, how changing the position of a force applied to the rod affects its rotation.
It's a powerful way to visualize abstract concepts. The document also highlights the simulation's embeddability within web pages. What are the implications of that?
That's crucial for accessibility and integration into existing learning platforms. Teachers can seamlessly incorporate it into their lesson plans, online courses, or even student projects. It makes the resource readily available and easily integrated into various learning environments.
The target audience is clearly students and teachers, but the HTML5 and JavaScript implementation ensures broad accessibility, right?
Absolutely. The use of HTML5 and JavaScript makes the simulation browser-based, eliminating the need for specialized software or plugins. This ensures compatibility across various devices and operating systems, making it accessible to a wider range of students regardless of their technological resources.
The document mentions the simulation's availability on various platforms, including Chromebooks, Windows, macOS, and mobile devices. This speaks volumes about its accessibility. What about the pedagogical approach?
The simulation's design aligns with modern pedagogical principles, emphasizing active learning and inquiry-based education. Students aren't just passively receiving information, they're actively engaging with the material, experimenting, and drawing their own conclusions.
The simulation is an open educational resource, OER, licensed under Creative Commons Attribution Share Alike 4.0 Singapore license. What does that mean for educators and users?
It means the simulation is freely available for educational use, allowing educators to adapt, modify, and share it. This fosters collaboration and allows for customization to suit specific learning objectives. However, it's important to note that commercial use of the underlying easy JavaScript simulations library requires a separate license.
That's a crucial point to emphasize. The document also mentions the Easy JavaScript Simulations EJS library. What role does it play?
EJS provides the framework for creating interactive physics simulations. It simplifies the development process, allowing educators and developers to focus on the pedagogical aspects rather than getting bogged down in complex coding.
The credits list Juan M., Agrigabiria, Fremonteng, and the Keng. Can you elaborate on their contributions?
While the specific roles aren't detailed, it's clear that these individuals played key roles in the development and implementation of the simulation. Their expertise in physics, programming, and educational technology contributed to the creation of this valuable resource. The link to Agriagabiria's website provides further insight into his work in physics education.
The connection to open source physics at Singapore is also significant. What does that organization do?
Open Source Physics at Singapore is a community dedicated to developing and sharing open source physics educational resources. Their involvement underscores the collaborative nature of the project and its commitment to making high-quality educational materials freely available.
How can teachers effectively integrate this simulation into their classroom?
The simulation can be used to demonstrate fundamental concepts like torque, rotational motion, and the relationship between force, distance, and angular acceleration. Teachers can design activities where students predict outcomes, conduct experiments within the simulation, and then compare their predictions to the results. This active learning approach promotes deeper understanding and critical thinking.
The document mentions several learning goals, but they aren't explicitly stated. What are some key learning objectives that this simulation can address? Students can learn to visualize the turning effect of forces, understand the concept of torque, and explore the relationship between force application point and rotational motion. They can also develop problem-solving skills by predicting and analyzing the behavior of the rod under different conditions.
The document mentions several related resources, including fault simulations and tracker video analysis tools. How do these connect to the falling rod simulation?
The mention of feet and trackers suggests a broader ecosystem of interactive learning tools. These resources can complement the falling rod simulation, providing students with a more comprehensive learning experience. For example, Tracker could be used to analyze real-world videos of falling objects, connecting the theoretical concepts explored in the simulation to real-world observations.
The frequent mention of AI in other simulations on the website is interesting. What does that suggest about the future of educational technology? The integration of AI in educational content creation is a growing trend. AI tools can assist in generating interactive elements, automating tasks, and personalizing the learning experience. This suggests a future where educational resources are more dynamic, adaptive, and responsive to individual student needs.
The document includes a quiz and essay questions. What purpose do these serve?
The quiz provides a quick assessment of student understanding of the key concepts. The essay questions encourage deeper reflection and critical analysis of the simulation's design, functionality, and pedagogical implications. They promote higher-order thinking skills and encourage students to connect the simulation to broader physics principles.
The quiz answer key is also provided. What's the value of that?
The answer key allows students to self-assess their understanding and identify areas where they need further clarification. It provides immediate feedback, promoting independent learning and self-directed study.
The glossary defines key terms like torque, Newtonian mechanics, and rotational equilibrium. Why is this important?
A glossary ensures that students understand the terminology used in the simulation and related materials. This is particularly important for physics, which has a specialized vocabulary. Clear definitions prevent misunderstandings and promote effective communication.
The sample learning goals for teachers are concise and practical. What makes them effective?
The learning goals are specific, measurable, achievable, relevant, and time-bound. This ensures that teachers have clear objectives for using the simulation in their instruction. They provide a framework for designing effective learning activities and assessing student progress.
The FAQ section addresses common questions about the simulation's purpose, accessibility, and classroom use. What's the value of this section?
The FAQ section provides readily available answers to frequently asked questions, saving teachers and students time and effort. It addresses common concerns and provides practical guidance on using the simulation effectively.
The FAQs also address licensing and modification possibilities. Why is this important?
Addressing licensing and modification possibilities is crucial for transparency and responsible use of the resource. It clarifies the terms of use and encourages ethical sharing and adaptation of the simulation.
Looking back at the entire document, what's the most significant takeaway regarding the falling rod simulation?
The simulation's success lies in its effective combination of simplicity, interactivity, and accessibility. It provides a powerful tool for teaching complex physics concepts in an engaging and effective manner, aligning with modern pedagogical approaches. Its open-source nature and broad accessibility further enhance its value as an educational resource.
And what about the broader implications for physics education?
The falling rod simulation exemplifies the potential of interactive simulations to transform physics education. By providing students with hands-on experiences and opportunities for exploration, these simulations can foster deeper understanding, critical thinking, and a greater appreciation for the subject. The increasing integration of AI in educational technology further promises to enhance the effectiveness and personalization of these resources.
That was a great discussion. Thank you for sharing your expertise.
I just really